Types of chemical bonds. What is a chemical bond? A chemical bond is the force that holds groups of atoms together and makes them function as a unit. What do bonds tell us? Well, bonds tell us a lot about the physical properties of particular compounds, like their melting points, boiling points, hardness, and conductivity. Bonds also give us an indication of what we call bond energy, which is the energy required to break a bond. So let's say we start with sodium chloride, and we put sodium chloride into water. We already know that sodium chloride is an electrolyte, so it will break up into sodium ions and chloride ions, where each of those ions will be surrounded by the polar water molecules. And in essence, what happens are electrons are transferred from the sodium atom to the chlorine atom in order to make those ions. But when the water evaporates away from that solution, the positive sodium ions and the negative chloride ions are going to be attracted to each other to form solid sodium chloride. So the question is, why does this happen? And the reason why this happens is because solid sodium chloride is at a lower possible energy by behaving this way. So what we're talking about when we deal with examples like sodium chloride are what we call ionic bonds. Ionic substances are formed when an atom that loses electrons easily reacts with an atom with a high electron affinity or a high attraction for electrons. And when that happens, we have a transfer of electrons which forms ions, hence the name ionic bonds. Ionic compounds generally result when a metal reacts with a nonmetal, when something on the left side of the periodic table reacts with something on the right side of the periodic table, or when we have atoms that tend to lose electrons reacting with atoms that tend to gain electrons. We can use Coulomb's law to calculate the attractive or repulsive force between ions. So it can be used to calculate the energy of interaction between a pair of ions. And to calculate the energy associated with the attraction of a pair of ions, our equation would be E equals 2.31 times 10 to the minus 19 joules nanometers times Q1 times Q2 over R, where Q1 and Q2 are the charges on the ions, and R is the distance between the ion centers. So if we look at this equation in general, as we increase the charges on the ions, we're increasing a number in the numerator of the equation, which is going to increase the attractive force. As the distance between the ion centers increases, we're increasing a number in the denominator of our equation. And by increasing a number in the denominator of our equation, we're decreasing the attractive forces. And we can actually calculate those forces. So calculate the energy of interaction between a magnesium ion and an oxide ion if the distance between them is 0.205 nanometers. So we have our equation. For Q1, we're going to plug in +2. For Q2, we're going to plug in -2. And for R, we're going to plug in 0.205 nanometers. So +2 times -2 gives us a -4. We'll divide that by 0.205, multiply it by our constant. The nanometers will cancel out, and we're going to be left with a negative 1.89 times 10 to the minus 19 joules. Now, we want to notice that the answer is negative. And what that tells us is the attraction between those pairs of ions will be at a lower energy when they're attracted together. Now, if we were to take two positive ions or two negative ions, that would give us a positive value for our energy. And that would give us the repulsive forces between like ions. Now, let's say we want to look at the bonding that occurs between two of the same type of atom. Let's use hydrogen as an example. There are a couple of things that happen when two hydrogen ions come close together. There are two unfavorable things that happen when two hydrogen atoms are brought close together. The electrons outside the nucleus of those two atoms are going to repel each other, and the positive nucleus is also going to repel each other. But at the same time, there's going to be a favorable term that occurs. The negative electrons of one hydrogen atom are going to be attracted to the positive nucleus of the other. So we've got two unfavorable terms and one favorable term that we need to come in or think about when we have two hydrogen atoms coming close together and bonding with each other. So let's look at this diagram. Along the x-axis, we have the distance between two hydrogen atoms in nanometers. And along the y-axis, we're looking at the energy terms involved with the net potential energy that results from the attraction and repulsion of the charged particles and the kinetic energy due to the electrons moving around. So if we were to look at this particular graph, towards the beginning, we're looking at when those atoms are very, very close together. And towards the end of the graph, we're looking at when those atoms are really, really far apart. Now, when the atoms are really, really far apart, there's really no attractive force between the atoms. As we bring the atoms closer together, we're kind of moving towards the left on this graph, the atoms start to interact with each other. And when we get to the lowest possible energy point, we're at the optimum distance with the lowest overall energy for the system. At that point, we're looking at what we call our bond length, or the optimum length between the two atoms. If those two atoms get too close together, then the repulsive forces start to take place. So the 0 point of energy is defined with the atoms at an infinite separation. At a very short distance, the energy rises steeply because of the importance of the repulsive forces as the atoms come closer together. And the bond length is the distance at which the system is at our minimum energy. So what we're dealing with are what are called covalent bonds. And they're the type of bonding encountered when hydrogen atoms and any other molecule in which electrons are shared by the nuclei. So we have two extremes that we've talked about. We've got ionic bonding, which is a transfer of electrons, where we form positive and negative ions that are attracted to each other. And we've got covalent bonding, where atoms share pairs of electrons equally. But there's a middle ground, what we call polar covalent bonds. Polar covalent bonds are formed when two atoms share pairs of electrons between them, like in covalent bonding, except that there's an unequal sharing of electrons in polar covalent bonds. So this is going to result in a partial positive and a partial negative charge. And we've seen this before when we talked about our water molecules. So if we look at this as an example, we've got molecules that contain hydrogen atoms and fluorine atoms. And there's a difference in electronegativity between hydrogen and fluorine, but they're going to share a pair of electrons. The fluorine has a greater attraction for electrons than the hydrogen does, so the fluorine's going to be partially negative, whereas the hydrogen is going to be partially positive. So if we take these molecules and we set them up into a magnetic field, we're going to see that all of the hydrogen atoms in those particular polar covalent molecules are going to be attracted to the negative side, and all the fluorine atoms are going to be attracted to the positive side. When will this happen? Well, it has to do with differences in electronegativity. And remember that electronegativity is the ability of an atom in a molecule to attract shared electrons to itself. So if we were to look at covalent bonds, since they're atoms of the same element, they have the same electronegativity, so they have the same attraction for electrons, so there's no polarity. But as we look at atoms that are of different elements, they'll have different electronegativities and different attractions for electrons. So when we talk about electronegativity, there's actually values that are assigned to particular elements based on their attraction for electrons. And Linus Pauling discovered this idea of how to determine electronegativities. He was a U.S. scientist. He won Nobel Prizes for chemistry and peace. And he developed a method for determining electronegativities. So electronegativities have been determined for almost all elements. And these values range from 4.0 for fluorine, having the highest electronegativity or the greatest attraction for electrons, and cesium with an electronegativity value of 0.7. So if we look at a table, we see our electronegativity values. And again, we're going to have a trend for electronegativities. Electronegativities increase as we go from left to right across the table. And again, we would expect that because the effective charge goes up, so the attraction for electrons increases. And it increases going up a group or decreases going down a group, because as we go up a group, the electrons are closer to the nucleus and there's a greater attractive force. So when we talk about electronegativity and bonding, generally, if the difference in electronegativity is 0, we have a nonpolar covalent bond. If the difference in electronegativity is greater than 1.67, we have an ionic bond. And if the difference in electronegativity is somewhere greater than 0, but less than 1.67, we're going to have a polar covalent bond. So bond relationships. If the electronegativity difference is 0, it's covalent. If it's kind of in the middle, it's polar covalent. And if it's large, it's ionic.